So I think we need to, let's see if I can make John a host also.
Oh, it's not turned on. Yeah. Send request.
I don't know. Bob N8REL, can you make John a co-host, please? There we go. So, John, you should be able to bring up any slides and ask the three questions.
Okay, only three.
Only three. We're going to
Yeah,
go easy tonight,
I
since
got
everybody
four,
is nice enough to show up for the extra session.
and yeah, I have four, and they're not um most of them math. Let's see how I did. Did you get the screen?
Yes, we did. Yes, we
Yes.
did. The screens popped up. The question's there.
And not the answer yet.
No answer.
And I even practiced these, so I know how to do them too. Um, so this is a not quite Ohm's law, but this is a basic equation. So the question is, how many watts are consumed when a current of 7 milliamps flows through a 1250 ohm resistance? 61 milliwatts, 61 watts, 11 milliwatts, or 11 watts. So they're stuck on 11 and 61 with some decimal point problems there. Um, so this is yeah, so you guys wanted some with math. This is the math one. If you remember the equation, maybe. Um, I don't know if we covered this very slowly. And the problem is it's a very common equation when you're uh, doing circuitry. It's the I squared R. Watts is equal to amps squared times ohms. I squared R. Um, we're always chasing I squared R losses, which are heat. Um, so if you square 7 milliamps and multiply that by 1250, any guesses? Well, I've been to talk about it a little more. So if a number is less than one, when you square it, it gets smaller, as opposed to if it's greater than one, like two, and you square it, it's four, which is bigger than two. But when you square 7 milliamps, it turns out to be 49 something.
49 milliamps.
No, I don't think so. There's less. You got to move it over. So it's 6 digits over. So it's really, I think, 49 microamps. But then you multiply it by 1250. So 49 times 1250 is where the 61 comes in. And you get back to the 61
Yeah.
mil. Yeah.
So it'd be
Looks like
six,
B.
would it be A then, 61 milliwatts?
Yeah. Yeah. I don't know if I can bring up
Put it
a
on.
calculator. If you want to do it on a calculator, is
Yeah, I was doing it on that one.
it's
007.
I think I moved the decimal correctly, and when I do, I get 61.25. So that would be approximately 61 milliwatts, right? Or
if you say so.
if
That is
I'm
the answer, yes.
if I'm moving decimals correctly, I'm not.
Yeah, you came out right there. Uh-huh. It's one of those. It's all about that darn decimal place. It drives engineers nuts. So that is correct. 61 milliwatts.
Milliwatts. Okay.
Yeah. Because it's 0.007 squared, which is anyways, here's another one. This one is tricky because it's not really it was in the manual. What transformer turns ratio matches an antenna's 600 100 ohm feed line impedance to a 50 ohm coaxial cable. Well, so you're trying to match 600 with 50. And we went through that pretty fast. If you remember, it's the ratio of the squares, I believe. We use this a lot to match antennas, basically.
Would that be D?
B, I think so. No, it's A.
A. Oh, boy.
7.1. Yeah, so it's boy, this is the one I didn't practice. It's the problem is it don't jump out of the manual when you read the manual. It's about a half a page is all they devote to it, and there's two questions that sometimes are on the test, and this is one of them that just kind of sneaks in on you if you so well, no, I'm wrong. It's not a square, is it? It's just the ratio. Is that how you got it? So 600 divided by 50 is 3.5. I don't
Nope,
Six,
nope.
600 divided by 50 is 12. So
Yeah.
Then you have to take the square root.
Yeah, there's a square involved.
The impedance ratio is equal to the square of the turns ratio. So if you turn that around, the turns ratio is equal to the square root of the impedance ratio.
Boy, I don't find the page number here.
yeah,
Okay.
I see 424 down at the bottom, but that's not,
That's where it is.
in my book.
Yeah, that's what I remember. They don't make a big deal out of it. There it is. Yeah, 424. Thank you, Kim.
So, but I don't see the question there. I do see some formulas there. Is that
That example,
36 or 37?
they're going from 600 to 500. So it's
Oh.
37. I think.
Oh, it is 37 because I see the numbers are the same there. Okay.
Yeah.
so it's 600 divided by 50, the square root of that, huh? Which is where you get to 3.5, I believe. Wish I had my calculator up here. But would that be right? So 60 divided by 5 is 12. And then the square root of 12 is 3.5, I believe. Just guessing. So 3.5 to 1. A. And so here's an easy one. I mean, while this is just plain memorization, what is the approximate open circuit voltage from a fully illuminated silicon photovoltaic cell? A solar cell. A single solar cell. Each cell is actually a diode, so that's why they talk about it open circuit. And this is just plain memorizing. I was going to say a clue is forward voltage on a diode is 0.7 volts, but I don't know if that'd be a big help because you probably don't know that number either. But it's close to 0.7.
Yeah, I think it's 0.5, isn't it? If I remember.
Right.
Yeah,
It is 0.5.
that was when I kept getting messed up on a practice test. So
Yeah. And well, if you work with transistors or diodes, 0.7 volt
Yeah.
silicon, and I don't know why this is that. Anyway, so that I'm gonna have to hand it over. Here's the one Wes wanted, but that's kind of one over the limit. If you want to go through this calculation,
Yeah, go ahead. Last one.
last one. What is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? And my editorial here is This is a trick question to me because it's peak to peak. So if you think you're a hot shot and you remember how you get from 120 RMS, if you remember RMS is 0.707 times the peak. So to go the other way, you divide 120 by 0.707, and that'll give you the peak, but that's not the question.
Yeah.
The question is peak to peak. So
Hmm.
I think it's D.
yes, yes, it is. Which really surprised me because I've had to deal with these voltages and I always remember the 169 for some reason. Anyways, that's all I've got. Thank God. Stump the teacher, huh? The square root. Thanks, Wes. And
Okay,
stop share, huh? There you go.
so now it's Marv's turn.
Well, let me see if I can get it up here. Uh, see. Okay, what do you guys
Okay,
think?
so Marv, you're on the wrong screen again. So stop sharing, please. Leave the slideshow going, but go back to the Zoom screen and stop sharing. Okay, so now click on share screen again. And one of the choices should be the slideshow. Or it's one where you just see one slide. There we go. Okay, my work is done.
Okay, so that's what you're seeing?
Loop antennas, 7.3
Okay,
blank.
all right. So, okay, we got loop antennas. Uh, a loop antenna could be circular, it could be square, it could be triangular. It could be any shape that is not too narrow. Uh, the feed the feed line can be attached to a break in the loop, or a smaller loop can be used to couple the RF energy to the main loop. So a square loop with each leg a quarter of a wavelength long is a quad loop. And you do see quad antennas from time to time. Now, triangular or delta loops are symmetrical with each leg a third of a wavelength long, and with an attachment point at a corner. One wavelength loop acts electrically like two dipoles connected end to end with the open ends brought together. They have a very omnidirectional pattern with the peak angles of radiation somewhat lower than a dipole at the same height. Let me get back to this for a second. I did want to mention one thing about them. As far as the loop antennas are concerned, a lot of guys use loop antennas for receiving antennas. So you would have an antenna for transmitting and a loop antenna for receiving. And quite often what you would do is set up two loop antennas and switch between the loops. So you would have the loops would be a little directional. So you would have you'd set them up in the directions you want to work, or you want to get and so then you would switch between them. And so you would get a switching mechanism that would work that way.
Yeah, loops are usually quieter, isn't that right, Marv? For receiving?
Yes, they are.
Yeah.
They are quieter. Now, there's a number of radios that are set up so that they have one 259 port that is just a receiving port. Now you do have to set up. Usually, you do have to set up a way to switch between those, so that when you're sending, you automatically switch out of the receiving antenna to your transmitting antenna. And there's ways of doing that. There's a are you guys under groups.io? Groups.io? Are you familiar with it?
It's a mail
Groups.io.
it's a mailing group thing, right, Marv?
It's not a mailing group. It's if you go into any browser and just put in groups.io, you can find forums for just about anything. If you're looking for a particular radio, for example, let's say you're interested in that ICOM 7300, and you're looking for what people have to say about it, or you're looking for help with it, you could find a forum for that 7300 by going to groups.io and then doing a search for the ICOM 7300, and you'll find a forum for it. Maybe more than one forum for it, because it's a popular radio. I have access to forums for my Yaesu and my Tentec that I use. And but as far as the loop antennas, there is a forum called Loop Antennas. So again, you go to groups.io through a web browser and do a search, and you'll find that. So if you're looking for example, if you're looking for information on a Yaesu FTDX 1200, you can find a group that's using that radio, and they're asking questions back and forth about it. Software, if you're using a logging software, there'll be a group that a forum that's dedicated to that logging software. I guarantee it.
Yeah, I use it for certain things. Kim's got her hand up.
Oh, no, I don't.
Oh, no, you don't? Oh,
I
okay.
think so.
Somebody does.
Um,
But you can ask questions too, right, Marv? That's
Yeah.
because then it gets emailed to everybody in the group, and I get questions like that, or you get to watch the dialogue between you, the person asking questions, and hopefully an expert.
um,
So anyway, on to quads and delta loop loops. I keep, sorry about that. I get troubles. There's a popular variation on the Yagi beams using a quad loop for elements. It has two or more full-size loops mounted on a boom. And they're approximately one wavelength in circumference and operate on the same principles of re-radiation and phase shift as does the Yagi. The driven element of the quad is about a quarter wavelength per side, and a symmetrical delta loop about a third wavelength per side. Quad and delta loop reflectors are about 5% longer in circumference than the driven element, and the directors are about 5% shorter. And the front to back ratio is generally better, a little better than the Yagi. Now, here's a representation of a quad of a loop antenna. Now, what's the advantage of a quad loop for HF? It'll fit into a smaller space on a lot. A Yagi for HF has a big swing. It can be 12 or 15 feet. It could have a radius of 12 or 15 feet. So if you're on a small lot, you could be literally swinging that antenna over your neighbor's lot. Okay. Some people might not like that, or there might be trees in the way or something like that. So you might want to use a quad, because a quad is going to be smaller and more compact. The disadvantages of it is if you live in an area with where you're prone to bad weather, like ice storms or heavy snows, they're fragile, and they can be damaged easily. There were a couple of companies that were making them a quad loop or a quad antenna that they claimed stood up pretty well to bad weather, but I did a kind of a search for them and I couldn't find them anymore, so I'm not sure they're still in business. Now let's go on to small loops. When the circumference of the loop becomes less than a third wavelength, the current in the loop becomes relatively uniform all the way around the loop. So if you look at image 710 in your book, and that's what we were looking at previous there. You can see how that works. It causes the radiation patterns to develop sharp nulls broadside to the plane of the loop. They're used effectively as receiving antennas and portable or low profile transmitting antennas. A lot of people in HOAs use them because they can put them out in their in their yard, and then bring them back in after they're done working, and then put them using them as a portable antenna. Or they can use them, they can go to the beach with them. People will use them on their decks, or they live in an apartment building or something like that. They could put them out on a balcony. So they have good uses. The only problem with them is that they're you got to tune them all the time.
Yeah, narrow bandwidth.
And as the comment there, they're good for direction finding. If you're into there's a sport involved with direction finding and fox hunting, and they use loop antennas. There's a picture of one there. If you take a small dipole and bend it in a circle or square, with the end separated by a small gap, you've got a halo antenna. It's not a continuous loop, but it's viewed as a halfway loop, and they're quite often used as a as a VHF antenna. They're omnidirectional as far as pattern is concerned, with a horizontal polarization. Now you could mount it on a car for mobile operation for 2 meters. Or I've never seen one used that way, but I guess it could be done.
Back in the 50s, I hear they did a lot before repeaters.
Is that right? I never.
Yeah, I saw one once that had come off a car for 6 meters.
Practice questions. Which direction is the maximum radiation from a VHF UHF halo antenna? Broadside to the plane of the halo, opposite the feed point, omnidirectional in the plane of the halo, on the same side as the feed point.
And they are horizontally polarized as opposed to a vertical.
So, I mean, the answer here is omnidirectional in the plane of the halo.
That's right.
Yeah. Yeah, C, omnidirectional. In which direction or directions does an electrically small loop less than a 10th wavelength in circumference have nulls in its radiation pattern? In the plane of the loop, broadside to the loop, broadside of it, and in the plane of the loop. Electrically small loops are omnidirectional. I guess.
Broadside to the loop.
Broadside of the loop. Yay! Broadside to the loop. You're right.
Oops, 7:15.
Okay. Specialized antennas, random wire antennas. The bane of my existence. A surefire way to get RF in your shack. It's not always practical to have a half or a quarter wave long resonant antenna, but so you could use a random wire. You know, in other words, just throw something out there and tune it. So you connect it directly to the output of the transmitter without a feed line. And here's the kicker. It may result in significant RF currents and voltages on the station equipment. I tried this once. I did a lot of sailing for many years, and I tried a random wire on my boat with a manual tuner, and this was my first experiment with using a rig on a boat, and I had a propane stove on the boat, and so I had in order to, as a safety measure, I had it was a sniffer, and it was a combined sniffer and an on and off switch for turning the propane off, and but it involved an electronic system for sniffing for propane gas. There was a sensor down in the bilge of the boat, and it would of course sound an alarm if there was a propane leak, because propane is heavier than air. It would settle down into the bottom of the boat. Obviously, if you had propane in the bottom of the boat and you got a spark, it'd blow the boat up. So anyway, I set this thing up, and I put this random wire up to the top of the mast, and I had a manual tuner, not an automatic, but a manual tuner. I was really doing it on the cheap, and I triggered the transmitter, and there was a shriek out of that sensor, and I blew the freaking thing right there. I mean, I just cooked that whole thing. It cost me about $125 to replace the thing. That was my first and last experiment with a random wire without an automatic tuner. I went on it. I did work out using a radio on the boat very successfully, but what I did was I went to a split backstay and insulated backstay and a automatic tuner, and it worked out pretty well. I worked all over the world with that thing. But getting back to this, you're gonna have a lot of problems if you use a random wire antenna. You're gonna have a lot. You could and probably will have a lot of problems with stray RF in the shack, and I would not recommend doing anything like that. Even though they say here you can get excellent results with it, I don't think it's worth the effort. That's why you could use an end-fed antenna, but you should make it like a wavelength, like you can make it 138 feet, and you're still going to have RF problems, but you could work those out. Usually using toroids and stuff like that, but you don't want to. I really don't recommend random wires. I really don't. If you look at 7.14 in your book, you can see the image stacked antennas, and it does give you more gain as you add more and more directors. The beam width of the main lobe between the points on the main lobe give you a greater gain. Vertical stacking the antennas increases the gain and narrows the elevation beam.
I hate to tell you something, but I have.
With a vertical stack with the antennas directly above each other, you space the antennas about halfway with a length apart. When you do that, the additional gain for a vertical stack of two horizontally polarized beams is about 3 dB. Here's that 7.14 stacked antennas illustration. So you've got a mast and you got a horizontal boom, and you've got the beams.
A beam like that, would you have the feed line connection on top or below? Or is that horizontal or vertical? That's horizontal.
What do you mean by on top or below?
Well, if the beam is horizontal, flatwise, there's a connector, right? PL.
I'm not following you.
I don't know.
He's asking where you attach the coax to the actual physical antenna. Your coax cable that you run up the mast.
I really don't. I'm really not sure because I've never worked with this kind of. I've never worked with stacked antennas.
Okay, no big deal. Thank you.
Yeah, you just try to keep them out of the, a lot of times we run them perpendicular to the elements.
Yeah.
So there is a thing called a log periodic. It's you've probably seen TV antennas, and those are log periodics, but they are essentially a long boom with the elements spaced out along the beam, along the boom in a specific method of spacing them out. The length of the spacing increases logarithmically from one end to the other. They're designed to have a consistent radiation pattern and low SWR over a wide frequency bandwidth, as much as 10 to 1. So it's a multi-band antenna. They don't have as much gain or front to back ratio as a Yagi antenna. Here's a image of one. Probably be pretty good for UHF, VHF. I used to know a guy that had one he used for HF, and it was a huge thing. I mean, it was when that thing swung, it was one big long antenna. Beverage antennas are used for receiving antennas. They were invented by a guy named Harold Beveridge. They weren't designed to have high gain, but to reject noise and interfering signals that aren't from the desired direction. So you've got low signal strength, but a great signal to noise ratio. So they're referred to as a traveling wave antenna. It's usually a long wire, usually as long as you can get it. And you put it fairly low, less than 20 feet high. And then you align it with the direction that you're hoping to get signals from. So they're used exclusively for directional receiving on medium frequency and low high frequency bands like 40 meters and 80 meters, 160 meters. So you've got high ground losses, and it's way too inefficient for using as a transmitting antenna. There's a diagram about it, what it looks like. You got to have a lot of land to put one of these up, or have very accommodating neighbors. But if you live in the country, it's a great antenna to put up. So signals arriving from the direction of the terminating resistor induce a traveling voltage wave along the wire transferred to the feed line at the feed point. So signals arriving from the other direction are either absorbed by the terminating resistor or do not induce voltage waves in the antenna. So it's a pretty nifty antenna. Multi-band antenna is what hams mean by a multi-band antenna is a design that can be used on a number of, obviously on a number of different bands. The most basic multiband antenna is a trap dipole. Each trap is a parallel LC circuit. It acts like a open circuit at resonance, and below resonance, it's like an inductor, and above, like a capacitor. At lower frequencies, the trap adds inductance to the antenna, and it makes the antenna look electrically longer. At higher frequencies, the capacitance electrically shortens the antenna. Here's a typical setup. What's the disadvantages of it? You're tuning it all the time. It has a very narrow space. In other words, let's say you're working on 15 meters over here, and you've set it over here. Let's say you're operating on you're on 21 meters, and or 15 meters, and you're at 21. So let's say you're on 2160, 21060. Let's say. Well, you move it a little bit. You move a little bit, and your SWR is going to go up considerably. So you're constantly retuning all the time. But they're great if you've got a small lot, or if you don't have a easy way to get supports up. Maybe there are trees or whatever you want to use for to support an antenna, or not in a convenient place. It's a perfectly reasonable, logical antenna to put up. This was a 4080 trap antenna. Was my first antenna, the first antenna I ever had. The lowest frequency of operation, the antenna acts like a regular dipole, shortened by the inductance of the trap. Now, Yagis also use traps to work on several bands. A 3-element tri-bander Yagi with traps in the elements works well at 20, 50 to 10 meters. In fact, I've got one. It's in pieces behind my garage. Drawbacks. Well, it works on multiple bands. It radiates harmonics and spurious signals. So you got to be careful when you're using it. So you're not generating those signals, those spurious signals. You got trap losses. So it reduces the efficiency of the antenna. It won't radiate as well as a full-size antenna, but I did pretty well with the one I had. I don't know if I told you guys this story. I hadn't been in radio very long, and I had that 4080 trap dipole, and I worked this guy, and I forget his call sign, but he said he was in Antarctica. So I'm talking to a couple of friends of mine who are in radio, and a couple of days later, I say, hey, I worked this guy in Antarctica. And they said, no way did you work this guy in Antarctica, not with your 100 watts and you're trapped diving. So I said, well, they said it must have been a pirate. So I let it go. I figured, well, you know, they're probably right. They'd been in radio a lot longer than me. So a few years ago, I happened to be going through one of my old paper logs, and I saw that record of that contact and the guy's call sign. So of course now, when I had done that, you know, we didn't have computers the way we do now, doing what we do now, and I would have had no way to look it up. So I said, well, just for the heck of it, I'm going to look up his call sign. So I looked up his call sign, and sure enough, he was a silent key, but during that time, he was working in Antarctica. So I did actually make a contact with him in Antarctica. Well, let's go on to practice questions.
Well, it's a little after 8 o'clock, so perhaps we can stop and take a break here.
Okay. So what is the characteristic of a random wire HF antenna connected directly to the transmitter? It must be longer than one wavelength. Station equipment may carry significant RF current. It produces only vertically polarized radiation. It is more effective on the lower HF bands than on the higher bands.
You said you complained about the RF current, so I'm going to go with B and Bravo.
Everybody agree?
Agreed.
You stressed that point pretty good.
That's correct. In free space, how does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically a half wavelength apart typically compare to the gain of a single 3-element Yagi? Approximately 1.5 dB higher, approximately 3 dB higher, approximately 6 dB higher, approximately 9 dB higher.
Three dB is the standard. Yeah, standard answer.
Yeah, I think it's 3. Yeah.
All right. Yep, it's B, 3 dB. What is the primary function of antenna traps? To enable multi-band operation, to notch spurious frequencies, to provide balanced feed point impedance, to prevent out-of-band operation.
Traps enable multi-band operations.
Yeah. Okay.
A. What is the advantage of vertically stacking of horizontally polarized Yagi antennas? It allows quick selection of vertical or horizontal polarization. It allows simultaneous vertical and horizontal polarization. It narrows the main lobe in azimuth. It narrows the main lobe in elevation.
Is it yeah. I think it's either C or D, but I'm guessing C.
Yeah, it's a good get. D narrows the
D.
main.
I
Okay.
knew it. I agree. I knew it was narrow, but I didn't know which one.
Yeah, I was trying to figure out which one. Okay.
You're a braver man than me.
Which of the following is an advantage of a log periodic antenna? Wide bandwidth, higher gain per element than a Yagi antenna, harmonic suppression, polarization, diversity.
B, higher gain.
A, wide bandwidth.
A, wide bandwidth. Okay. I gotta stop. I'm missing them all tonight.
No, it's better to try.
Periodic antenna. Element length and spacing vary logarithmically along the boom. Impedance varies periodically as a function of frequency. Gain varies logarithmically as a function of frequency. SWR varies periodically as a function of boom length.
Okay. Okay, I can't be wrong 3 times in a row. I think it's A, element length and spacing.
Yeah, it's A. Element length and spacing vary logarithmically along the boom.
Yeah.
What is the primary use of a beverage antenna? Directional receiving for low HF bands, directional transmitting for low HF bands, portable direction finding at higher HF frequencies, portable direction finding at lower HF frequencies.
Yeah, it ain't portable, so I don't think that's one of those answers. A, I think. Again.
Directional receiving for low HF bands. Which of the following is a disadvantage of multi-band antennas? They present low impedance on all design frequencies. They must be used with an antenna tuner. They must be fed with open wire line. They have poor harmonic rejection.
D?
I was thinking between B and D. I picked so.
Want to take a shot here, or what did we say?
D is in delta. They have poor harmonic rejection.
Yep.
Yeah, okay.
All right. Let's go on to Feedlines. Characteristic impedance. Balanced feedlines consist of 2 parallel conductors separated by insulating material in the form of strips or spacers. They have different characteristic impedances that characterize how electromagnetic energy is carried by the feed line, and that's different from resistance. For parallel conductor feed lines, the radius of the conductors and the distance between them determine Z. The characteristic impedance. The most common type is window line. And window line is usually 450 ohms. But the common characteristic impedance for coaxial feed line used by emitters is 50 ohms and 75 ohms. So window line is the stuff over here, in C here, that's window line. A and B are stuff you probably have seen as, if you've ever fooled around with TV antennas. But these are fairly common, you'll come across, you'll use, commonly you might frequently use something like 450 ohm window line, or 300 ohm, or center to, like D, or any of these you might use. They all have their advantages. They have disadvantages. The feed line transfers all of its power to an antenna when the antenna and feed line impedances are matched. If impedances don't match, some of the power is reflected by the antenna. So you got forward power is the power traveling toward the antenna, is reflected power is power reflected by the antenna. Power in a feed line is reflected at any point at which the impedance of the feed line changes. That could be at the antenna, that could be at a connector, or from any type of feed line, or from a different type of feed line. So what's SWR? The wave carrying forward power and reflecting power form stationary patterns inside the feed line. These are called standing waves. The ratio of the peak voltage in the standing wave to the minimum voltage is called the standing wave ratio, SWR. It measures how well the antenna and feed line impedances are matched. 1-to-1 is a perfect match. None of the power is reflected. SWR equals infinity, indicating that all the power was reflected. And SWR is always greater than 1-to-1. And except, for example, it's always, for example, it would be 3-to-1 and not 1-to-3, or 1.5-to-1 or 2-to-1.
Oh.
So SWR is equal to the ratio of the higher of antenna feed point impedance or feed line and characteristics impedance to the lower. Example, what is the SWR in a 50 ohm feed line connected to a 200 ohm load? 200 divided by 50 is 4-to-1. Not a good ratio for a radio. What is the SWR in a 50 ohm feed line connected to a 10 ohm load? 5-to-1, 50 divided by 10. It can be measured anywhere along the feed line. And it's most commonly measured at connection transmitter. But sometimes that's not the best thing to do. Sometimes it's better to measure it, if you can, at the antenna. You measure it by using an SWR meter. Sometimes they call it out the bridge. Let's see if I can show you one here. So, I don't know if you can see this. Here's a SWR meter.
I have an inline SureCom SWR meter that shows the ones you're talking about, the transmit, output, the reflection, if any, and the match.
It varies along the wire too. So if you add a longer wire, it'll change. So that's why Marv says measure it at the antenna is the best starting point.
Transmitting equipment is designed to work at full power with an SWR at the input to the feed line of 2-to-1 or lower. Antennas that are much too short or too long will not work well and will have extreme feed point impedances causing high SWR. How do you match it? Matching feed line and load impedances, such as with an antenna, eliminates standing waves from reflected power and maximizes the power delivered to the load. But not always. The impedance of matching is more often done at the transmitter end of the feed line. That's why you use the tuner. The devices that we use to reduce the SWR are called impedance matchers, transmatches, antenna couplers, and antenna tuners. But they are not really tuners. They don't tune the antenna. They only change the impedance of the antenna at the end of the feed line to match the transmitter. In other words, an antenna tuner increases the power transfer from the transmitter to the feed line. So you've got devices constructed from inductors and capacitors that are adjustable by the operator. The T circuit can match a wide range of impedances at the feed line connection to a 50 ohms that matches transmitters to match the transmitter. It's important to remember that the SWR in the feed line between the impedance matching device and the antenna doesn't change. The device just changes the load going to the transmitter. The SWR in the feed line stays the same. In other words, if you've got an antenna that's not resonant, you can tune it so that it works with the radio, but it's still not resonant. So here's a T network. Here's a diagram of a T network. So you've got the antenna going to an impedance matcher to the transmitter. So you've got a T circuit. So a T network is designed to be used with unbalanced coaxial feed lines. This circuit uses 2 variable capacitors and 1 variable inductor. This is a fairly common network. It's been used for forever, actually. The output of the T network can be inductively coupled to the output so that neither of the feed line conductors is connected to ground. The thing though is that you need to get your antenna as close to a 1-to-1 as you can. That's why I was suggesting that you need to do it at the antenna first, because yeah, you could tune that antenna you know, with your automatic tuner, if your radio has one, if it can make the match, or you could use a manual tuner, but you could have losses that are so bad that you're really not getting a good signal up. You know, you're just heating up the coax or the feed line. So it's incumbent on you to do everything you can to get that antenna trimmed and balanced so that it's working, you know, at the antenna. Feed lines dissipate a little of the energy they carry as heat, called attenuation or loss. Loss is measured in dB per unit of length, usually dB over 100 feet. Loss increases with frequency for all types of feed lines. The smaller the cable diameter, the higher the loss. So increasing the SWR in a feed line also increases the total loss. So you got two things working there. When you're putting up an antenna and you're looking for feed line, you got to be careful. Look at the specs on your feed lines, and get the lowest loss feed line that you can get, that you can afford. It's well worth it. Especially when you start working with QRP rigs. You know, when you're running 5 watts, you don't want to lose 3 watts to your feed line, or 4 watts to your feed line. The higher the feed line loss, the lower the measured SWR will be at the input to the line. Practice questions. What is the purpose of an antenna tuner? Reduce the SWR in the feed line to the antenna, reduce the power dissipation in the feed line to the antenna, increase power transfer from the transmitter to the feed line. All these choices are correct.
C.
C, increase power transfer from the transmitter to the feed line. Which of the following factors determine the characteristic impedance of a parallel conductor feed line? The distance between the centers of the conductors and the radius of the conductors, the distance between the centers of the conductors and the length of the line, the radius of the conductors and the frequency of the signal, the frequency of the signal and the length of the line.
That one is A, I believe.
Yep. Distance between the centers of the conductors and the radius of the conductors. What is the relationship between the high standing wave ratio, SWR, and transmission line loss? There is no relationship between transmission line loss and SWR. High SWR increases loss in a lossy transmission line. High SWR makes it difficult to measure transmission line loss. High SWR reduces the relative effect of transmission line loss.
I'll jump in. It's B.
That's what I think.
B.
Mhm.
One thing I should also mention, another reason why you want to get your SWR down, it's hard on a radio. Uh, I think.
You can blow out finals, huh?
Yep, it's hard on the finals. And if you happen now, a modern rig will shut down if you get over a 3-to-1 SWR, it's going to shut down. But if you happen to buy an older rig that doesn't have those modern conveniences, you could well blow your finals. Now you got to get it fixed.
How do you define modern, I guess would be my question. How new before that
Oh, geez.
That's a good one, Marv.
That is a good one. Let's see.
No,
I'd say if you buy a radio that was made before 1980,
okay.
Kind of the quality of the design too. Some
Yeah.
radios are more tolerant than others.
The reason I was asking is my brother, one of my brothers is a silent key, and he had an old ICOM from the mid 80s, I believe. I was just curious.
Yeah, that's why they held on to tubes for so long. They were a little more tolerant
Yeah.
in the final.
if you have a tube type radio, I guarantee you that you're going to have that issue. You're going to have to be very careful with it.
Yeah. Okay.
What is the nominal characteristic impedance of window line transmission line? 50 ohms, 75 ohms, 100 ohms, 450 ohms.
450 ohms. I remember that one.
Yep, I remember that one too. Yeah.
Yeah.
What causes reflected power at antenna feed point? Operating an antenna at its resonant frequency, using more transmitter power than the antenna can handle, the difference between feed line impedance and antenna feed point impedance, and feeding the antenna with unbalanced feed line.
C.
Yeah. See,
What?
C is in Charles.
Charlie? Isn't Charlie? C isn't Charlie.
Yep.
Yeah.
Feed line impedance and an antenna feed point impedance. How does the attenuation of coaxial cable change with increasing frequency? Attenuation is independent of frequency. Attenuation increases, decreases. Attenuation follows Marconi's law of attenuation.
E is in boy.
B, yes, attenuation increases. In what units is RF feed loss usually expressed? Ohms per 1,000 feet, decibels per 1,000 feet, ohms per 100 feet, decibels per 100 feet.
D is in delta.
Yeah, D is in delta. What must be done to prevent standing waves on a feed line connected to an antenna? The antenna feed point must be a DC ground potential. The feed line must be an odd number of electrical quarter wavelengths long. The feed line must be an even number of physical halfway lengths long. The antenna feed point impedance must be matched to the characteristic impedance of the feed line.
sounds like D delta.
Yeah, I agree. Joe.
Yep. If the SWR and antenna feed line is 5-to-1, and a matching network at the transmitter end of the feed line is adjusted to present a 1-to-1 SWR to the transmitter, what is the resulting SWR on the feed line? 1-to-1, 5-to-1, between 1-to-1 and 5-to-1, depending on the characteristic impedance of the line, between 1-to-1 and 5-to-1, depending on the reflecting power of the transmitter.
B is in boy, it doesn't change it, right?
Right, it doesn't change.
Yeah.
It just what is the standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load? 4-to-1, 1-to-4, 2-to-1, 1-to-2.
A, 4-to-1.
Yep, A, 4-to-1. What is the standing ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
D, 5-to-1.
Yeah, 5-to-1. That's it, folks.
Hey.
Da, 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 da.
Okay.
Hey,
Yeah.
thanks for doing this.
Yeah, I appreciate it. Thanks for the special session.
Yeah.
I thank you guys for being willing to do it.
Yep, especially the sleep deprived.
Yeah. Yeah.
Yeah.
Yep, I'm a little that. So.
How's the tooth? How's the tooth?
I got up at
Good. Good.